Good morning, ladies and gentlemen. May I have your attention, please? Thank you. So brand new for the BC curriculum, right, is the logistic differential equation and general form of the solution to a logistic differential equation. And so what is, all right, our population P, right? How does that rate of change vary? Well, it varies jointly with respect to the amount of the population itself and some limiting factor, that is the difference between the carrying capacity and the current population. So let's go ahead and translate that using M for the carrying capacity of the population, P for the population itself, and T for time with constant variation K. So what does that look like, dP dt, as a general differential equation? Vivian? Absolutely. Raise your hand if you have the same as Vivian. K times P times the difference between M and P. Good job. Now, my general form solution to a logistic model, right, can be solved algebraically, right? We can solve that algebraically and generate P equals. Now, that utilizes the technique of partial fractions, which we now are equipped to handle, but we can skip right to the general form if you remember that from our activity. What would that look like with K's and M's and T's? Marissa?
M over 1 plus A e to the opposite parentheses K times M, and then times T.
Awesome. All up in the X, where A is some constant that we can determine using a given condition, just like we have with solutions to other differential equations, right? A does not equal the initial value the way that it does in our A-PERT formula, y equals y naught times e to the kt, right? That A is not the same as my initial value, but it can be determined using an initial condition. Let's do that for our second part. So let's go ahead and suppose now that our carrying capacity M is 240 individuals and that our constant variation is 0.001. Let's find the particular solution that satisfies P of 0 equals 40. So this would be at time t equals 0, the start of the problem. 40 individuals are in the population, yes? Okay, so we'll start with our general form that Marissa just gave us. P is given by M over quantity 1 plus A times e to the opposite of K M T, and we'll go ahead and use our given condition along with our carrying capacity and value of K to determine A, that constant, right? We don't know what A is, so we can't pin down the particular solution, but we certainly can then rewrite this and figure out what A is. So at time t equals 0, there are 40 individuals. The carrying capacity is 240. Don't know what A is yet, but we're going to figure out what it is, times E to the opposite of K is 0.001 times M is 240. Close. T is 0. And so we see that this whole exponential term, e to the 0.001 times 240 times 0, it just is e to the 0 is just 1. And so we see that this denominator becomes 1 plus A. So it looks like 40 equals 240 over 1 plus A. We can multiply the 1 plus A over quantity, divide by the 40, and it looks like I'm getting 6 equals 1 plus A, or A plus 1, so I must have the value of A is 5. Raise your hand if you have A is 5. Great, and we'll do a quick rewrite. We're not done. We still need to write the particular solution. Now we know what it is. It is P equals 240 over 1 plus 5 e to the opposite of, and now we'll go ahead and put those back in. It'll be what's 0.001 times 240, so is it just 0.24? 0.24 T? Is that everything? Okay, go ahead and raise your hand if you had that. So who had the particular? Way to go, you guys. And so we now have a logistic model. We saw what that looked like in our activity where we exhibit exponential shaped growth in the beginning, and then we taper off in the rate of growth, still positive, right? Still positive, but tapering off as we approach that carrying capacity, that value of M. That's pretty cool. Okay. So where does that leave us? Well, that leaves us with more space in case Mr. Fritz needed it, and we wanted to solve from the differential equation. I wasn't sure if you guys wanted to solve with dp/dt and go all the way. In any case, now let's go ahead and pause the recording and get you credit for your OTL number 3. Okay, ladies and gentlemen. So we saw the general form for a differential equation for a logistic model, right? dp/dt, where P is my current population and M is that carrying capacity. I included this in case we wanted to generate that general form that you supplied for your Bellwork. And so we could do that using the technique of partial fractions. However, I know that in number 17, you started from the ground up and generated that as well. So we're going to leave this here for the time being. We can certainly return to it, but I do want to make sure that we investigate our quick and dirty area and volume review that's on tap for today. So I'm going to go ahead and leave this here, and I'm going to go right to our area and volume review. Today our objective is to remind ourselves how we can use the technique of definite integration in order to find the area of irregularly shaped regions and the volume of irregularly shaped solids, space shapes, right? So we're going to go ahead and spend today reminding ourselves how to handle that, and then it's my goal that you'll have some time to work right together on your OTL and clear those cobwebs. The BC includes all of the AB area and volume, including both this washer method and then the known cross sections, the ones that were kind of like paperweights that weren't spinning around anything, but were just, the base was the some defined region, and then we knew what cross sections taken perpendicular to the base were. We had to write an area function and integrate across the range of possible slices. So that's what we're going to do today, and we're going to do it all in one day, because that's how good you guys are. All right, so we're going to use our graphing calculator today in order to generate pictures. That's what I'm going to do here. But please pay attention on your OTL to the gray exercises versus the regular exercises. So the gray ones are you're supposed to non-calculator, and that's what I'd expect. And then the ones that aren't gray, those you can use your calculator to determine like points of intersection. The math 9, right, if you need to do that, and so on and so forth. All right, let's go ahead and get cracking. Find the area of the region bounded by the given curves. And we're going to consider y equals x squared, x plus y equals 2, and y equals 0. So let's go ahead and get a good picture of that. I think for this one I'll actually be able to do it okay. So I know that that x plus y equals 2 is y equals negative x plus 2, so I'll photograph that. And the y equals x squared, I know what that looks like too, so I'm gonna go for it. So I know my y equals x squared. In blue is the parabola whose vertex is at the origin 0, 0. And go standard steepness, out 1, up 1 squared, out 2, up 2 squared, out 3, up 3 squared, so we can get a nice picture of that. So I'm looking at 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. So we have a nice picture of our parabola in blue. Our green function y equals negative x plus 2, we know that is negatively sloped line, slope of negative 1, y-intercept of 2. Let's do that in green. So it'll be right here, and down 1 over 1, down 1 over 1, down 1 over 1. You can even go backwards, up 1, and get a nice picture. And y equals 0, where's y equals 0? So I went and made this huge graph, and the only part I need from it is right here. See what I'm saying? Well, I was going for that reason, but That's all right. Let's see if we can't group that. So I want the area of this region right here. Yeah, is that it? We can figure out what that is. I wonder if it's gonna let me. Oh, it is gonna let me. That's pretty cool. All right, so we'll go ahead and consider, right, a typical rectangle drawn in that region, oriented vertically so that I can scan the region from left to right and see, does the top of the rectangle touch the same boundary curve regardless, right, regardless of where I draw it? Well, no. If I draw that rectangle over here, the top boundary curve is the line. If I draw the rectangle on the left-hand side, the top boundary curve is the parabola, right? And so if I were to integrate with respect to x and scan the region from left to right, I'd have to set up not one, but two separate integrals. Come with me for a moment on a magical mystery tour of the mind, if you will. If I were to draw instead a horizontally oriented rectangle, right, that spans across the region there from left to right, does the right side of my rectangle touch the same boundary curve no matter where I draw it? Does the left side of the rectangle touch the same boundary curve no matter where I draw it? So the point of this example is to remind you to be purposeful in your selection of which variable you'll integrate with respect to. I'm going to set up a definite integral that integrates from the bottom to the top of the region, and then I can do it in one integral. To keep the height of my rectangle positive, my horizontally oriented rectangle, to keep that height positive, I'll do right curve solve for x minus left curve solve for x, and I can do it in a single shot. So my area in general will be given by the integral from lowest y value c to highest y value d in the region. F of y is the height of my rectangle. dy is the infinitely thin width of my rectangle. And I can keep f of y positive by solving my right curve for x equals, with y's in it, minus my left curve, boundary curves, solve for x with y's in it, and that'll ensure that it stays positive. All right, so let's do it in one shot. The lowest most y value of my region is 0. The greatest most y value of my region is what? 1. I can keep the height of my rectangle positive by doing right curve. Right curve solves for x is x equals what? 2 minus y minus my left curve. What's my left curve solve for y? My left curve solve for x would be the blue parabola would be x equals plus or minus square root of y. And I would want which one? I would want the positive one because I'm there in the first quadrant. Yes? So minus x equals positive y. Blue. dy. Awesome. Now that I've set up my definite integral, I'm ready to evaluate this, right? And we could do this exactly and algebraically through use of the fundamental derivative calculus because I've had antiderivatives for all those. If I didn't, right, and on your assignment there's a couple that you don't have antiderivatives for, you can just math 9 it. Either one is fine. The key here is focusing on our setup and the concept behind it. All right, so I'm just going to do this one quick because we can integrate 2y minus y squared over 2 minus power rule, right? Y to the 1/2 current exponent goes to y to the 3/2. Dividing by the new exponent is dividing by 3/2 is the same as multiplying by 2/3, right? Y to the 3/2. Evaluated from 0 to 1. You down? Awesome. And we can do this nicely because my upper limit is just 1. So it looks like 2 minus 1/2 minus 2/3 minus 0 all the way through would be 0. And I'm left with 2 minus 1/2. Oh, goodness. So this is 12/6. No. Yeah, 12/6, take away 3/6 is 9/6, take away 4/6 is 5/6. Is anybody else getting 5/6? Yeah, Danny. Danny got it, that's good enough for me. Awesome. So, the point of this example was, if I'm purposeful in the selection with which variable I'll integrate with respect to, then I can save time and energy and reduce the number of depth intervals. Now, could we have done this with respect to x? Yeah, we would have just had to break it up into two separate integrals, right? Because my boundary curve on top changes depending upon where I draw it. All right, I'm giving myself room to work and I'm never using it. I was thinking ahead yesterday. This day, falling behind. Let's consider the area of the region bounded by the given curves. We've got y equals the square root of x equals y plus 2, and y equals 0. All right, so I want to make sure that I'm being purposeful in the selection of my variable to integrate with respect to, and this is the same boundary line, isn't it? Same boundary line. So this guy is y equals x. Oh no, it's not. We're positively so. So x minus 2. Keep going here. So if I were to rearrange this, I get y equals x minus 2. Is that right? So my green linear equation would yield up 1 over 1, up 1 over 1, up 1 over 1. Okay. Y equals the square root of x is restricted to only to the right of, right? To the right of the y-axis because it only accepts positive, or I'm sorry, I should say non-negative input values. So 0, 0, 1, 1, and 1, 2, 3, 4, 2. So our square root of x function, we should curve back down, but. And y equals 0, where's that? Well, y equals 0, then it'll be down here, downtown, Jimmy Brown. So everybody see our region? Pretty sweet. So I'm now going to group it, make it bigger. Awesome. Okay. So let's go ahead and consider for a moment. Integrating with respect to which variable makes the most sense. Go ahead and quietly tell your partner and be ready to explain why. So we're going to integrate with respect to x or with respect to y based on our region and how come. It's like Mr. Fritz. Why? Why do you ask? No, the variable. All right, guys. Time's up. So, which variable are you going to integrate with respect to and why? Tyler and Vivian.
Why?
Why? Because we need to find the area. Sorry, had to. Who else picked y? Who's going to use y? Okay, and so why did you select integration with respect to y for this particular region? Grace and Marissa?
Okay, so because you can do right minus the left curve the whole time, you don't have to break it up.
Absolutely. If I draw a horizontally oriented rectangle, right, then I can touch the right-hand side of the region bounds the same curve regardless of where I draw that horizontally oriented rectangle, right? Versus if I had drawn a vertically oriented rectangle, then depending on where I draw that, I have a different boundary curve on bottom. If I draw it on the left versus if I draw it on the right side of the region, the bottom of the rectangle touches a different boundary curve. Therefore, I'd have to set up two separate definite intervals. And so instead, I would encourage you to integrate with respect to y So we'll draw a typical rectangle, again horizontally oriented. I'll keep the height of that rectangle positive by doing right curve solve for x minus left curve solve for x. Integrate over the region of possible rectangles, bottom to top, and then get my area. So we can jump right to the definite integral, I think. I know my area will be given by the integral from the lowest most y value looks like 0 in red to the greatest most y value is not 4, but what? 2. Good. Right curve minus left curve. So my right curve, solve for x, would be x equals y plus 2. That was in green, so I'll use green. My left boundary curve, solve for x, would be x equals y squared. And I'll go ahead and do that in blue, and this was with respect to y. Awesome. Again, we know antiderivatives for each term of my integrand function, so I'll go ahead and jump right to the fundamental theorem of calculus evaluation theorem, where I find an antiderivative y squared over 2 plus 2y minus y cubed over 3, evaluated from 0 to 2, and that lower limit of 0 will make this easily evaluated without a calculator as well. We'll go 2 squared is 4 over 2 is 2, plus 2 times 2 is 4, minus 8/3, minus the lower limit evaluated in my antiderivative function all the way through is just 0, so I'm getting 6 minus 8/3. That would be 6 times 18 minus 8/3 is 10/3. Awesome. Awesome. And we did it without a calculator. Cool. What questions do you have about our area review so far? Okay, so then we'll do one more area, and then we'll switch our discussion to include volume type questions. So find the area of the region bounded by the given curves. Oh geez, y equals x cubed and x equals y squared minus 2. I'm trying to picture what this is going to look like. And so to do that, it might be easier for us if I go ahead and add that 2 over, and then solve for y. Looks like y will be given by the positive and negative square root of x plus 2. So it looks like we've got a sideways parabola that's been shifted to the left 2 units. Okay, to the left 2 units. Good. Opens to the right. On top, y equals x cubed. I'll do that in blue. All right, let's go ahead and see if we can't get a picture of this region. Top curve, I'm going in blue. Y equals x cubed has key point 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. And so we get that serpentine curving S shape that we've come to know and love as our cubic parent function. Let's see if that's enough. Our second boundary curve in green is sideways parabola, opens to the right, vertex shifted to the left 2 units. Let's try that. So here we go. So here, if I plug in negative 2, 0, then I get 0, negative 1 would be 1. You guys getting that? And negative 1? Yes? And because the steepness factor on here is just a 1y squared, I know through transformations that I could go 2 out 2 and 4. So I'm going to try 1, 2, 3, 4 to do this analytically. That's pretty sweet. All right, I'm going for it. So you guys know I checked to make sure I had the emulator at the ready. But so far, I haven't had to go to it. We're going crazy, aren't we? Where's our regions? In between the right-facing parabola and the cubic function looks like, Is that what you guys are getting? All right, decision time. Go ahead and decide with your partner this time what makes the most sense. Be ready to share with the whole class.
Who? Where?
How?
Because you can't plus or minus square root of 2. Also, you don't know plus.
Why is it funny?
Why is that? Why is that so funny? Why is that not? All right, guys. Verdict. Sydney and Kobe.
Why?
And why didn't you choose to integrate with respect to y instead of with respect to x?
Because then you're only using the two lines, and you still might have to split it up between plus or minus, positive and negative wise.
Oh, yes, yes. If we did a vertically oriented rectangle, and I draw on the left-hand side, I'd have to, right? I'd have to use a different boundary curve on the bottom until I got over here, right? Then I'd be using the cubic on the bottom as opposed to that negative square root. And so I think we can do this quickly and more efficiently if we draw a horizontally oriented rectangle as well. Are we 3 for 3? I think I meant to bring up the first one and say, oh, but what if we had done it with respect? Next time. Next time. That's all right. We'll do it with respect to y. It's good practice because with respect to x, it's easy. So ordinary. So no matter where we draw the horizontally oriented rectangle, the right side touches the same boundary curve, right? And the left side touches the same boundary curve, so it's more efficient to integrate with respect to y. Again, we just need to figure out these points of intersection. It looks like -1, -1. Yes? And, uh-oh. That's the kicker. What's that point? Right? So we're going to have to do more in order to figure out that point. That's when y equals x cubed hits that. I think that's why I pulled the emulator. And so let's go ahead and see if we can figure out what that point of intersection is before we can evaluate this. So what will we do? Well, we'll go ahead and determine that point of intersection graphically. In our graphing calculator, however, we will have to enter our equation, solve for y in the y equals menu. So which radical, right, will I use, the positive or the negative, to determine that point of intersection? The top one, right, the positive because we're up above. So let's go ahead and do that. And my window, I'm going to go -3, -3 to 4. And I'm going to go -2 to 3. All right. So I might not like that window, but we'll see anyhow. And we need x cubed. I like the shortcut math 3 buttons. Pretty print. And we need the square root of quantity x plus 2. And we need a pretty graph. You know, guys, while I'm here, I can't resist. I want to just add really quickly opposite of vars, y vars, function, y2, just so that I have the whole shman. You know what I'm saying? I want the whole shman. What's that, Mr. Fritz? You want it all? And you want it now? Yes. I want it all and I want it now. Is that too much to ask? So there we go. There's our region. Did everybody see our region? So what are we going to do now? We're going to do second, calculate, intersect, fifth option. And we'll do first curve, second curve, guess. Only one. Hey! Cool. So make sure that you're keeping all those decimal places so you don't compromise accuracy. Only round to the AP College Board 3 places at the final end. That way we know that those 3 decimal places are going to be correct. So we're going to go ahead and store that value in our grapher. So which one do we want? Do we want 1.21486? No, we want the y coordinate. So we want the 1.79300037. I'm going to call that D. Now I'm going to integrate from -1 to D of what? Right curve minus left curve. Right curve is the blue. X equals cube root of y minus our left curve is x equals, this time we need parentheses, y squared minus 2, close, and with respect to y, how do we do? Awesome. So I'm going to go ahead and store that in my grapher and do math 9 since we've already gone to our calculator. So what do I need? I need 1.7930037. What do I do? Store and alpha D. All right, so here we go. Math 9. We're going to integrate from -1 to alpha D of right curve was cube root of y, so we'll do cube root of x. Math 4 shortcut. Yeah! It's little things. Okay, so little things. Minus left curve. Solve for x, and I'll do parentheses again so I don't mess up. Would be y squared minus 2 with respect to y, but my variable just keeps telling me x. And just all and grinding. I thought I stumped it for a minute. No, Tyler, not like homecoming, like computer trying to figure it out. So 4.215 would be correct to 3. 4.215, is that what you guys are getting? Awesome. So did you guys get that? Did you guys get the same thing? Yeah. And we have to keep 3, right? We have to keep 3. Of course, when we're talking about the area, right? The area, we would be talking about square units, but I've seen on the free response scoring guidelines, right? They typically just put the number. They don't put square units necessarily, so I'll just leave it as 4.215 now. What questions do you guys have about our quick and dirty area review? All right, so we're going to switch gears now and go up a level and up a dimension. And now consider not the area of an irregular shaped region, but what about the volume of an irregular space shape, right? A 3-dimensional solid. So we're going to go ahead and look at 3 different types today. First, let's suppose that we have a static object. The base of a solid is the region in the first quadrant, bounded by y equals 2 sine x over an interval 0 to pi. Cross sections taken perpendicular to the x-axis are semicircles. Let's find the solid's volume. So this is representative of a typical cross-sectional area type problem where we find the volume of a solid with known cross sections. Okay, and so this is something that you have to do. In fact, there was one on that same practice exam for BC that I looked at last night. So what are we going to do? Well, first we need to be able to visualize this so that we can consider our area function, a of x, of a typical slice, and then integrate that area function across the range of possible slices to generate the overall volume. In order to do that, we need a picture. So let's go ahead and see if we can draw the base bounded by y equals 2 sine x in the first quadrant from 0 to pi. So we'll go ahead and go first quadrant. And from 0 to pi. Halfway in between will be pi over 2. And I know that sine of x from 0 to pi, sine of 0 is 0. Sine of pi is 0. So I must have intercepts at 0, 0, and pi comma 0. At pi over 2, sine is equivalent to 1 times 2 is 2. So on the y-axis, I need to go up at least 2 tick marks. So at pi over 2, y equals 2 times sine of pi over 2 is 2 times 1 is 2. Is everybody getting, we've got one arch here, kind of the top part of an arch of my trigonometric graph. Do I see it? So we're going to let this be the base of my solid. And now we're going to go ahead and draw a typical cross-section taken perpendicular to the x-axis. So what would that look like? Well, there's our proverbial calculus machete. Whack! Right, if I were to take a cross-section perpendicular to the x-axis and turn it to face me, what would its shape be? Well, it would be a semicircle coming up out of the page. So I need to write an area formula for my typical cross-section, rearrange that area formula as a function of x, and then integrate it across the range of possible slices. So how do I want to visualize this? Well, it could be coming out of the page as a semicircle. A semicircle coming out of the page. If I turn it to face, it would look like this. Now we need to write its area formula. So what's the area in general of a semicircle? Well, a whole circle is pi r squared, so a semicircle would be 1/2 pi r squared as a formula, yeah? Where r would be the radius of the semicircle. Where on my picture is r? Well, on my picture, is r that red line segment? No, r is only the radius of that semicircular cross-sectional slice. So it's only half of that red line segment. It's this blue part of it right there. That's my radius right here. You guys good? Are we up to the challenge of writing an area function of one variable, a of x or a of y? Yeah, because my slices are perpendicular to the x-axis, am I going to use x's or y's in my formula? Sophia and Danny? I've got to do x's this time, right? We'll integrate it from left to right with respect to x. Good. So I'll rewrite this as not an area formula, but an area function of one variable, x, and go ahead and see what r is in terms of x. So I'll keep my 1/2. I'll keep my pi. But I'll rewrite my r, right, in terms of x by considering the relationship with my original base. I know that blue boundary curve was given by y equals 2 sine of x. So the blue boundary curve is y equals 2 sine of x. No matter where I draw that, the radius of my semicircle is half of the diameter of the semicircle, which is given by the function value y itself. Therefore, my radius is half of 2 sine of x. Well, what's half of 2 sine of x? It's just sine of x. And so we see that, right, the 2 sine of x, my original y equals function, is the diameter of my semicircle. Half of that then would be my radius of that semicircle. So it looks like when I go to integrate my area function across the range of possible slices, I'll use 1/2 pi sine of x squared. So I'm getting 1/2 pi sine squared x. Is that what you guys are getting? Yeah! All right. So let's go ahead and do it. We'll integrate. I feel like this region should be shaded. Do you guys feel like maybe this thing pepper shading? You know what I'm saying? I added, UW Baraboo Stock County, a night class now that's focused on shading to try and help with our pictures and our visualization. So that, the drive's kind of a pain when the weather's bad, but just positive incremental steps, self-betterment, that's what it's all about. Let's do it. So we're going to set up our integral, our volume B in general, right, is given by the integral of my area function of a typical cross-sectional slice multiplied by its infinitely thin width gives me the volume of one little slice. And if I sum up all of those individual volumes, I'll be left with the volume of the entire solid. So in general, I can find the volume of a space shape by integrating our known cross-sectional area function across the range of possible slices. In this particular case, I'll be integrating from 0 to pi. My area function a of x we just determined was 1/2 pi sine squared x. And I'm integrating that with respect to x. Okay, so what do we do now? Well, do we have an antiderivative for sine squared of x as it's written? Do we know what an antiderivative for sine squared of x is? What? No? Yes? Maybe? Symbolically not yet, right? Symbolically not yet, but that's okay. We're going to math 9 it in our grapher. Just make sure you're in radian mode, right? We've got to be in radian mode. And we'll generate it using our numerical integrator. So we'll go ahead and do mode. Make sure you're in radians for the AP curriculum. And we'll integrate math 9 from 0 to pi 1/2 pi where did I get the pi from? Oh, from the area of a circle. Okay. I'm like, why do we have a pi in there? We're not even doing solid revolution yet. So sine squared x. Oh gosh, we have to be careful how we write that. So I'm going to do sine of x squared. So I'm going to do sine of x squared with respect to x. So let's take a minute and see how many times I messed that up. Just my sine of x squared. All right, we're going to try it and see if we get the same thing. So who else got 2.467? 2.467? Yeah! I'll count that as a victory. Hey, one second. All right, ladies and gentlemen. Not only will we be asked to find the volume of solids with known cross sections and some predefined base, we'll also generate a solid by taking some predefined region and rotating it about some axis of rotation and considering the three-dimensional space shape that results. So let's consider the volume of the solid bounded by the given curves, and let's revolve it about a particular axis of rotation. In this case, let's consider the region bounded by y equals 3 root x over 4 and x equals 4. So let's consider what this picture is going to look like. So I'll go ahead and take a look at the picture. I'm going to go from clear, clear, clear. Y equals 3 times the square root of quantity x over 4, close quantity, close radical. And I don't know what this looks like. I know it'll be something like a square root, and I want to go all the way to x equals 4. And so what I'm going to do is inspect my original graph and change my window accordingly. So I want to go to x equals 4. So it looks to me like I can leave my y min. I think I'll shorten up my x min a little bit, and I need more x's, and I want more y max. So I'm going to go ahead and try -2 to 6 for both x's and y's and see if that's a good picture. If it's not, I'll just change it. Are we going to be able to tell what the solid looks like? I want to make my y min lower too. I'm picky. That's all right. Ah, that's a nice picture. That's a nice picture. Okay, so I'll take this one. All right, guys. So what are we doing now? Well, we're going to consider the solid that results when we take this region bounded by y equals 3 square root of x over 4 and x equals 4 and revolve it about the axis of rotation x equals 4. Can we visualize what that's going to look like? Yeah, let's go ahead and draw the solid result. So first, original region, 1, 2, 3, 4. Very good, original region. Now we're going to revolve it about that vertical line, x equals 4, and consider the space shape that results. What is it going to look like? I'm trying to grab the green. Yeah. Flip it. Yeah. Oh, Mr. Fritz, that's cheating. Yeah. But you cheat so good. Look at that. So it looks like we've got a nose cone kind of, right? Or a Hershey's Kiss that got left on the top of the cookie in the oven just a little bit too long and kind of melted down a little bit. Do you see it? Do you see it? I'm hungry. Get in my belly. I'm always hungry. Gosh darn it. I look at that and see food. What do you see? All right.
An igloo.
So let's go. An igloo, yes. An igloo. So let's go ahead and consider then, right, if we were to take a cross-sectional slice perpendicular to my axis of rotation. In this case, my axis of rotation is the vertical line x equals 4. Therefore, a cross-sectional slice will be flat, horizontal in nature. And we're going to integrate with respect to y. So a typical cross-sectional slice, right, would be, well, like a disc, wouldn't it? You guys see that? If I were to take that, excuse me, cross-sectional slice and turn it out to face, right, to face us, it would be the shape of a circle. And I use blue. And I'm going to draw my original radius by connecting my axis of rotation to the original region. So it's not over here, guys. Don't draw over here. This was a shadow region, right, that I got by cloning and flipping. The original one is where we're always going to connect it because this is a ghost curve that I created. We want to use the original function, so always connect your axis of rotation back to the original region boundary curve, and that'll keep our radius positive, okay? Great, so where is that? Well, it's right here. The process will be the same. I'll write an area formula for my typical cross-sectional slice. In this case, it's a circle, so the area formula is pi r squared, and I just have to figure out what my red r line segment is in terms of my original functions. So let's go ahead and rewrite this as area function, and it's not going to be a of x because we're going to integrate from bottom to top in this solid. We'll do a of y, which means that I need my line segment to be solved for. I hope this isn't about homecoming. So we're going to use my line segment, right, and solve for x. So how are we going to do x? Well, we need to take this curve, and we need to solve that for x equals. So what will we do? Well, how about divide by 3? So divide by 3 and square it, and times by 4, last. So you're getting x equals 4 times quantity y over 3 squared? Yes?
Yeah.
Cool. So my a of y will be kept positive by making my radius r right curve solve for x minus left curve solve for x. Let's do this together. So here I have my a of y is given by pi r squared, where my right curve solve for x is that vertical boundary line, x equals 4. You guys see that? Minus my left boundary curve, right, is that green Was originally a radical function, now it is x equals 4 y over 3 quantity squared. So, I mean, we could leave it like that, but I'm going to have to enter my calculator. So I think I might do 4y squared over 9. Are you guys okay doing 4y squared over 9? Then I can do it in my calculator without parentheses. You guys okay?
Yeah.
Awesome. And now we can go ahead and now we can go ahead and integrate that across the range of possible slices, right, in order to get the volume. So let's do that. I know my volume V will be given by the integral from least most y value to greatest most y value of my region, the area of a typical cross-sectional slice with respect to y. In our particular case, that's given by the integral from least most y value is what? 0 to greatest y value is 3. Awesome. So we'll integrate from 0 to 3. And my area is pi times 4 minus 4y squared over 9 with respect to y. And I put the pi in front of this because in the AP, if it were multiple choice setup, not integrate, oftentimes they have that pi out front. I'm going to math 9 it, and I'm going to do it exact. What? I'm going to go for it. I'm going to leave the pi out front and then add it in the last. So let's go ahead and see what that will generate. So here we go. On my home screen, I'm going to leave the pi out. I'm going to math 9 0 to 3. Right, let's see, a of y is 4 minus 4y squared over 9. Did we ever square it? We didn't ever square it, so we need the squared. Right, we need the squared right here. So right here I need the squared. Yeah, yeah. Is that everything? Does that fix it? So in here, I'm going to need back to 4. Should we go for it? So I left out the pi because I want to do it exact. And then I'll put it back in on top. Yes, are we ready? Are we ready? Survey says, math 9. No, math frac. Yes, so 128 pi over 5. Can we do that? 128 pi over 5. And that's exact. Now, we could have certainly put the pi in the original and go straight to a decimal, or we could change this into a decimal on my home screen, depending upon what the nature of my multiple choice, right, selections are. If they're decimals, right, you put the pi in. If they're exact, then you leave the pi out, and you can make that decision, right, based on your responses. Cool. What questions do you have about that solid revolution? All right, let's go ahead and do one more. So what happens when our region, right, isn't bounded by my axis of rotation? So consider for a moment, if you will, the original region bounded by y equals cosine of x, y equals sine of x, and x equals 0 in the first quadrant. And we're going to revolve it about the axis of rotation, y equals 0. So everybody, let's go ahead and consider x equals 0, y equals cosine of x, and y equals sine of x. Let's see what that looks like. And so I know at x equals 0, my blue cosine function is 1, yes, 1. And I know at x equals 0, my green sine function is 0. And I know that sine and cosine are equivalent at what x value? Pi over 4, right? Pi over 4, the value of sine and cosine are both root 2 over 2. So I know, and that's about 1.414, and so I know that here is x equals pi over 4, we'll say. And I know no 0 point. Right, there's my sine on the way up. So notice how our original region, right? Our original region bounded by x equals 0 is the y-axis, sine of x and cosine of x. Notice how it doesn't bound the axis of rotation. What? Well, the axis, I mean, it touches it, but one of the edges of it, right, doesn't run along it the entire time. So when we rotate this about y equals 0, right, we're going to get what kind of solid? Well, what is that going to look
like? Hershey's Kiss with a bite.
Yeah, hungry again. Strange looking bundt cake. Let's go ahead and call them that. You say bundt cake?
We can't say that.
Can't say that at school. Bundt cake. You know, like those molds, like those Jello molds or whatever with the ring on it.
They said butt cake.
See? Now you know why Tyler's getting called out in the hall, man. Mr. Governor. Unbelievable. Hey, I'm trying to flip this. All right, so here we go. Let's go ahead and consider the solid results. And now we're going to go ahead and draw a typical cross-sectional slice. And so here, Danny mowed down on our Hershey's Kiss. Not to be confused with and consider the solid results. So what's that going to look like? Here we go. It looks like a cross-sectional slice, thwack, taken perpendicular to my axis of rotation, is going to be not a circle, but what? What's that called?
A washer.
Yeah, a washer, right? It's going to be a washer. I know. No, back to food, thank you. Or a donut. Yes, or a donut. So, let's do that. So here we go. We'll take that cross-sectional slice and we'll turn it out to face us. And when we do, it looks like a donut or a flat washer. And we now need to write an area formula for that washer. All right. So we need to get our original curves in here and some line segments to get the radii, both outer and inner, for this cross-sectional slice. So I'm going to go ahead and use green here for this inside one. That would be something like this in my picture. And I'm going to use red for my outer radius, a red line segment. That would be like this. Yes? Can we do it? I know the general form for the area of this washer slice is given by A equals pi r squared minus pi r squared, where r is my outer radius and little r is my inner radius. And if I can write this as a area function, a of x, and integrate across the possible range of cross-sectional slices, I'll get the volume of this strange partially eaten Hershey's Kiss. All right, let's do it. So we'll set up my definite integral. After we generate a of x is given by pi times, what's my outer radius? Is red squared And my red function is which? Cosine? Cosine x? Minus pi r squared. And my inner radius was sine of x? Yeah, sine of x? Alright. So let's go ahead and do one more rewrite. We'll make a of x, factor out the pi, and we'll say cosine squared x minus sine squared x. Yes? Turns out we could do this analytically by applying a trigonometric identity, a double angle formula for cosine, but that's okay. We'll just do math 9 in the interest of time. We can do math 9 with our area function from 0 to pi over 4. And I'm going to do pi out front. And it's cosine squared x minus sine squared x dx. Yes? All right, let's do it. I'm going to leave the pi out again. I'm going for it. Math 9, 0 to pi over 4. And cosine squared x, do I have to do that? Square root of that? I'm going to be safe. Are you kidding me? I don't even do math practice. 1/2 times pi over 2. Pi over 2. You get that? That's sweet. Oh, almost took it bigger. Pi over 2. Good and bad. Crazy.
Why can't you do the radius as like cosine minus sine? Because I just did it and it didn't work. But like,
Yep. Great question. So what's up? Why can't we do, are you saying, oh, in the original before the squaring, or are you asking why we can't do squared apply the squared?
why can't the area be pi times cosine minus sine squared?
Great question. So if I look at my original circle, right, if I look at my original circle, I'm not taking this, that would be this distance right here that is not shown. That would be a blue distance here.
Oh, okay.
And that would be the circle that results from a radius of that length. But I'm not. I'm doing the whole circle with red radius minus the whole circle with green radius in order to give me the blue part that remains. You see what I'm saying?
Mm-hmm.
Good. Good question. All right, so pi over 2, raise your hand if you got pi over 2. Awesome. Can we close it up? I think we can. So, given an irregular shaped region with boundary curves, T of x for the top curve and B of x for the bottom curve, the area is given by the definite interval from what to what of what minus what with respect to x. Given the same region with boundary curves L of y and R of y, the area when integrating with respect to y is given by the definite interval from what to what of what minus what. And not 1, not 2, but 3 general forms. And so the first one I just want in general, volume B is given by what with A of x? In the second two, I want you to consider disk method versus washer method, and I have to change this or I won't sleep well tonight. There we go. You guys ready? Can we do it? Can we do it? Okay, so what would my d of x, my dx with respect to x area look like, Tyler?
The integral from a to b of t of x minus t of x.
The integral from a to b of t of x minus p of x for top curve with x is minus bottom curve with x is. Raise your hand if you have the same as Tyler for number 1. Keep your hand up if you can share number 2. Number 2, Kobe.
The integral from c to d of r of y minus l of y.
Nice. That is right curve with y's in it minus left curve with y's in it. Nice job. And general form for the volume of a solid with known cross sections, that would be the integral, right? The integral of my area function a of x with respect to x across the range of possible possible cross-sectional slices. General form with disk, that's the integral of what? Sophia?
The integral from a to b of pi.
Absolutely. So we have some general, right, area of a circle function, and we'll integrate that across my range of possible slices. Versus washer, what would washer look like? What would washer look like? Danny?
The integral of pi big R squared minus pi little r.
Absolutely. And so oftentimes we'll see that pi factored out in front. You guys are awesome, but I have to let you know the OTL isn't set in stone. It's on Moodle right now, and I put it up this morning, and I didn't have a chance to do the file yet. And so you have to check Moodle to see what the OTL is. I might change it during contact time slightly to take off a couple of problems, right, and swap them out for a washer problem. So once again, I might change the Moodle a little bit during contact time to better reflect our discussion today, right? Does that make sense? Awesome. Thanks, you guys. Great work today. I'll go ahead and save the recording.